I'm welcoming our next speaker, Andriy Mulyar. Is Andriy? Yeah, I can see Andriy. Hello, Andriy. Andriy, you're on. You're live. Hello.
Hello.
Glad to see you. Glad that you join us today. And so, let me briefly introduce you. Andriy is a co-founder and CTO at Nomic AI, a venture backend startup that is on a mission to democratize access to powerful artificial intelligence. Prior to Nomic, Andriy was an early engineer at Rod AI, where he trained multi-billion parameter MML LLMs to assist radiologist and PhD student at New York University, current Institute of Mathematical Sciences, and he cares about making AI systems and the data they are trained on more accessible to everyone. So, and the today's talk is about how to build a GPT for all. So, Andrei, the stage is yours.
Awesome. Thank you so much. Hi, everyone. Nice to meet you. I'm really excited to be here today. Talking at this conference means a lot of things for me. So I'm originally from Lviv, Ukraine. I moved to the U.S. when I was pretty young, but sort of like got my start in technology pretty early, and a lot of it was motivated by just being a Ukrainian and being an immigrant in a new country. So kind of want to start out with saying like really excited to be here today. So what we're going to be talking about is how to build a GPT for all, how to build a local large language model that you can use to run yourself, to not have to use third-party services to interact with one of the most powerful technologies that exists today. So a little bit about me, as my introduction sort of was given. So I'm the CTO and co-founder of a company called Nomic. Nomic, we basically build tools that make AI more accessible, everything from the data to the models. And obviously, I'll be talking more about the model side today. So, a little bit of an outline here we're going to talk about. So, I want to give a brief and very incomplete history, the kind of history that if a researcher was to see, they would laugh at. But a brief and incomplete history of large language models, pretty much starting at 2018. I'm going to ignore everything that happened the 30 years before there. I'm also going to talk about how to make these models, these kind of models that you see when you interact with chat.openai.com or Anthropic's models, run on low resource devices that might be akin to something like a toaster. So things with like 4 GB of RAM, small amounts of CPUs. I'll talk about how you can go about making these models, the kind of data that needs to go into them, what these models sort of look like, and sort of the kind of tips and tricks needed to be able to do to the actual end models to make them run on low resource devices. And then finally, I'm going to talk about some of the new developments that we've been working on, specifically at Nomic and with the open source community that we have around GPT4All, to make these models more accessible for everyone who has maybe not the most top of the line GPUs, maybe not the most top of the line CPUs, and some of the sort of low level infra and optimization work we're doing on the modeling side. And then finally, I'll say some words about what it means to sort of get access to models like ChatGPT, the same kind of quality as ChatGPT, but on your local devices. We're not there yet, but there's a couple of steps that the world can take to get there, and I'll talk about those. So, like I said, I'm not going to start in the 1980s. I'm going to start in 2018 with the famous paper that came out of Google called "Attention is All You Need." This paper is the paper of the transformer deep learning architecture. This is the machine learning model, the machine learning algorithm that produces a model that powers systems that you see like OpenAI's GPT models and ChatGPT, like you interact with online. And so this paper was created by a bunch of researchers, a couple of students that were all working at Google Brain at the time. And it turns out that everyone saw what they had created. Originally, this paper was to create a translation system, a machine translation system that would go in and translate from one language to another. It was a state-of-the-art way to go in and do that in 2018 at the time. And all these people saw that, oh my God, wow, we have just invented a new engine that allows computers to manipulate text, to transform text from one form to another without human intervention in the middle. So what did they all do? Well, they all ran out and they left Google and they all started their own startups. A lot of these startups are now worth billions of dollars. Adept by Ashish Vaswani, he's actually no longer there, but they right now, they recently actually released a model called Persimmon, which is a competitor to Llama. Character AI, which many of you may have interacted with, it's one of the largest consumer-facing chat GPT powered apps out there. Cohere, worth billions of dollars by Aidan Gomez, he's the CEO of Cohere, and so on and so forth. So these people in 2018 saw what they had built. Łukasz Kaiser, also at OpenAI now. These people saw what they had built. So I just want to tell you, like, there's a rich history that started way before November of 2022 of these models existing, and people knew that this technology was coming 5 years ago. And to sort of show you this is sort of like a build on the previous slide I was just showing you. This is sort of a rough family tree, very very incomplete, of everything that happened post this transformer paper, post this invention of this technology that let computers manipulate text to perform arbitrary tasks. So a lot of these companies now, like Perplexity, spinning out of some students from NYU and other places, it's one of these large chat engines that you can use to interact with the internet semantically, for example. And to talk a little bit about how models have developed over the last few years. So this is sort of like the timeline, starting at the invention of the transformer model and the kind of large language models that have been released sort of historically. So after 2018, this was really the first time in deep learning history and really machine learning history that computers got exceptionally good at being able to perform tasks with text. This task wasn't always generation. It wasn't just generating text. It was being able to arbitrarily go in and create models that can do text classification or extract relevant entities from text, for example. So the first generation of models after 2018, they actually weren't as powerful for doing text generation. Models like BERT, which was a pre-training strategy over top of the transformer architecture, allowed computers. So like most text systems you see right now deployed that do like text classification or extraction of like named entities like person, places, and things out of documents of text, most of those automated systems, they're built over architectures like BERT, which are based on the transformer. But as the years progressed, especially with the GPT-2 model and the GPT-2 decoder-only transformer that came out of OpenAI in early 2019, increasingly it was realized that you can use text generation as this universal interface for making computers do tasks with text. So what this means is that you can go in and say, with a prompt, extract out all of the following objects from this document of text, or use this document of text and summarize it for me. And then instead of doing a typical machine learning task where you have to do a classification over like 4 or 5 categories, it would open-endedly generate out a sequence of words which would match one of those categories. So that was sort of like this big paradigm shift that happened in about 2018, 2019. And then after that, as you can see, there's a giant blow up. Several organizations, several entities are going through and releasing models that are open source, that everyone can build on, everyone can access. Not all of these are text generation transformers. You have models like DALL-E, which are all based on the transformer architecture, come into existence. You see here in 2021 and 2022, where a lot more industry starts getting involved. Things like Anthropic's models come out. Google starts releasing models. But there's an issue. What happens in about 2021 and 2022 is people start realizing that the moat behind these sort of models are the data and the size of the models that goes into them. And what starts happening is this really big trend that existed for the past 20, 30 years in machine learning starts to break. The fact that models are being openly released for people to build on and openly access. And this sort of coincides with the size of models as well. So the chart that you're looking at right here on the y-axis, it's logarithmic. You see here where we're going on multiples of 10. And this sort of shows you the size of the models ever since the release of the transformer architecture. This is number of parameters, number of 32-bit floating point numbers inside of these models. So with GPT-2 in late 2018, 2019, these models were roughly in the 100 million to 1 billion parameter scale. That's only like 1 to 3 gigabytes of size on disk. And what happens is every single year, every 6 months, the average size of the most state-of-the-art machine learning models goes up an order of magnitude, multiplies by 10 in parameter count. And what happens in about 2021, 2022, people start experimenting with models that are gigantic, trillions of parameters. It goes down a little bit after that. There's several technical reasons why maybe trillion parameter models are not feasible to actually use and have diminishing returns into their actual productivity. But the sort of key point here is that these models got gigantic. And these sort of gigantic models, you can't really do much with them if you're not hosting them behind servers in front of an API. They're just too big. They require a machine that's super expensive to run, GPUs that cost you $50,000 per card, and several of them to even run the single model. And moreover, they're super expensive. These models cost millions of dollars to train and create, especially at this 100 billion parameter size. And so, sort of all of these trends sort of come together: increasing model sizes, increasing access to data, increasing industry interest into this technology, sort of resulting in this world where there's a few entities who sort of hold access to the top models that exist right now. And this was really the case up until about March of 2023. And of course, this I sort of mentioned this a second ago, but part of scaling up these models means you need a lot more compute. So this thing I'm showing you in front of this picture you see right here. This is a picture of NVIDIA's H100, or this is actually an A100, but same thing. A100 DGX box. So this is a machine that holds 8 GPUs. The cost to buy one of these boxes was at the time in 2020 about $200,000. The latest chips are about $500,000. In order to train one of these models, one of these big boys right here, in order to get one of these models out, you need about let's see, 300-400 of these boxes all linked together. So as you can see here, the cost of these data centers to even train models of this size, right, they go up astronomically, really limiting the potential for the kinds of people who have access to even thinking about and playing in the game of creating these models. It really cuts out in research labs and academia who just don't have the resources being backed by venture capital firms gives you access to, for being able to go in and play this game of creating the best in class large language model. And because of this, what happened is there's a few organizations now that exist: OpenAI, Anthropic, Cohere. There's a few more now. I made these slides a few months ago, updated them for this presentation, who have access to these actual models. The best world-class models, the best large language models that you can use to perform arbitrary text manipulation tasks, the things that are dominating the way we interact with information online today, they're owned by a few closed source organizations: OpenAI, Anthropic, Cohere. And in order to have access to this technology, the only way to do it is to go through one of these organizations. I'm going to argue in this presentation that this is a terrible way for the world to go. The access to the world's most powerful machine learning systems should not be held behind closed doors, especially behind closed doors that are managed by a small group of people in some suburb of San Francisco. And there's also other issues with centralization of these systems. Oftentimes, it makes it difficult for enterprises to get access to them. So what happens to your personal corporate data when the only way to access the most powerful machine learning systems to feed the data into are owned by a few companies? What happens when the values of these companies don't align with the kind of values that you have? Right. So there's several examples where companies like Samsung, who send their chip designs into OpenAI, had their chip designs trained on, and billion-dollar chip designs were getting spit out by ChatGPT to everyone else in the world who was using ChatGPT. Right? If I was to go into Samsung and steal their chip designs and publish them to the world, right, I would get sued into existence. If OpenAI does it, or if an organization that had a policy at the time to train on the data that they were getting that was put into their system and released out into the world through these models did it, it was a slap on the wrist. And also Italy. This has obviously been overturned. This is an article from April 4th where a lot of these developments were happening: March, April, May. Italy was one of the first companies to ban it. It since has unbanned it, but there is a lot of sort of there's a lot of issues when technology like this is only accessible through a few parties. So this all goes to say that there's many things going on that are sort of non-competitive in this space. There are many organizations that really feel like the direction that AI needs to head is that AI needs to be closed source, because the ability the ability to control what these models do, the ability to control the risk behind these models, cannot be managed by the general world at large. And there's only a select group of people who get to say what these models can and can't do, and who get to interact with them. And this is really profound. And this is actually an excerpt from the GPT-4 paper as it was released in March. OpenAI originally was a company that would go in and release all of their machine learning models openly. They were originally a nonprofit that was funded to do this. They since changed what they do. And this line right here that I highlighted, given both the competitive landscape and safety implications of large-scale models like GPT-4, we're not going to release any details about what the model looks like. We're not going to release details about what the model was trained on. We're not going to release how expensive it was to train. And most importantly, we're not going to release the data that went into it. This is sort of a thing that people have since been able to find out. There's lawsuits against OpenAI right now around the kinds of data they put into the models. I'm not going to talk about my opinions on anything of those. But as you can see here, there's an increasingly closed nature of the top industry AI companies when it comes to model release. So this all goes to say about what this talk is about. This talk is about the opposite of all of that. It's a stand against this idea that AI systems need to be closed source in order for humans to be able to safely access them. This talk is about GPT4All. So GPT4All was a project that I had started out in early March at Nomic, and this is this whole idea behind let's try to be a sort of a foil to what's happening in the space. In early March of 2023, it was the case that if you wanted to interact with a Chat GPT-like system, you needed to go through OpenAI servers to do it. And so what we did is we created a demonstration that the world does not have to be this way. We went in and we trained a 7 billion parameter large language model distilled from OpenAI's Chat GPT model. So we went in and we gathered examples of input and output from OpenAI's Chat GPT model. And we open sourced it. Open source is not just the data that it was trained on, the millions of examples that we were able to sort of distill and scrape from ChatGPT, but additionally the code to be able to train that model yourself, and the code to be able to run that model locally, meaning it could run on a machine with only 4 gigabytes of RAM and 2 CPUs, a machine that was disconnected from the internet. And the sort of to give you the sort of general arc and plot line of the whole story, what happened is it blew up. Within a day, we became sort of the third fastest growing GitHub repository in GitHub history. We reached, I don't know, it was like 20,000 stars within the first 2 days. We were at like 52,000 stars in the repository right now. There's about 50,000 people using the code ecosystem to run their own large language models locally on their own machines. And the rest of this presentation tells you about how you can go about doing this yourself. So what is GPT4All? GPT4All is the easiest way to run local large language models on sort of any computer, whether you only have CPUs, whether you have GPUs, whether the GPUs are not the most expensive ones. It supports all of it. So the question here, before I go in any further, is how powerful can a local LLM be, right? These models are obviously smaller. They're trained on less data. So what can they do? Well, I'm just going to pull up the actual chat client. This is sort of a open source binary that's built from GPT4All, and you can go in and run the models yourself. So I'm going to ask it. This is a 3 billion parameter model here that I have in the dropdown. You can go to the GPT4All.io to download the same chat client yourself. It's completely open source. You can read all the code underneath. It's built by dozens of people, and I'm going to ask it, write me a short story about giving a presentation at Devoxx Ukraine. So if I turned off the internet right now, which I'm not going to do because you guys wouldn't be able to see what I'm doing, all of this would work the same way it works right now. And what you see right now is this model generating all on my computer. So I have this current presentation software running. I have a bunch of things plugged into my computer. And what it's doing is it's generating text all locally. As you can see here, there's some biases still installed in this model, the kind of thing that you get from OpenAI. But it can generate text at 55 tokens per second, all on my MacBook that I'm currently running it on. And this is all sort of in real time, this demo I just showed you. So these models themselves can be pretty powerful. As you can see here, it's able to maintain sort of like coherence as it writes. It knows about Devoxx Ukraine. Oh, it doesn't know about Devoxx Ukraine, and it's able to write a story, probably hallucinating facts about it. This is a pretty small model. It's only 3 billion parameters. There's larger ones. There's code models in here, but I'll get into later the other kind of models you can use. But most importantly, I'm going to show you how you guys can build one yourself. So this is kind of just giving you a quick demonstration about what you can do with these types of systems. How powerful can a local LLM be? And so this is basically how you do it. You need a couple of ingredients. The first one is what model you're going to use. you'd be silly if you didn't go about and use the transformer. The whole introduction to my talk was about this history of this transformer architecture, all the crazy stuff that went on the last 4 years, and what you can do with them. But there's kind of a few tips here. So the first one is you want to stick with a decoder-only transformer. They've pretty much won the general-purpose large language modeling game. So the decoder part of the transformer. So this is the entire transformer architecture right here. The decoder part is this block right here on the right. So GPT-2 was sort of like the first large decoder-only transformer that was proven to be hyper effective in the tasks that it could do. And now most models that get released out there, these things that you see like right now, Llama or Falcon or MPT that you might see on Hugging Face if you're in the ML space or you're a software engineer dabbling with ML models. This is the architecture that these models are based on. And with GPT4All, just to give you an example, most of the models that are able to run sort of efficiently locally on hardware that isn't some hyper-intensive server hardware you have to rent from a cloud provider, the models are around 6 billion to 13 billion parameters. They come with various flavors of licensing. Most of these sort of best models right now, thankfully, we have access to Apache 2 licenses. Back in March, when we were working with the GPT4All, there was not a single decent model out there, apart from T5 and GPTJ, which actually had commercially licensable weights. What this means, you can run them in a commercial setting. So they were kind of more truer to the sort of definition of what an open source machine learning model can be. And one of the first things we did was actually we trained GPTJ. So the first model we trained was a Llama base. So Llama is that non Apache 2 licensed GPL. It was a GPL licensed architecture that permitted commercial use. We trained that model. That was the first GPT4All model that was released in this local LLM ecosystem. We then trained GPTJ. GPTJ was an Apache 2 licensed model. And because of that, people can go in and were able to go in and run that model in like commercial settings. But all being able to have access from the sort of code ecosystem that we have in GPT4All. So the kind of first ingredient to making your own local large language model is you want to use a transformer decoder. Don't go thinking about anything else. The other one is sort of instruction tuning data. So if you go right now to a platform like Hugging Face, what you'll see hundreds, actually thousands of local large language models that you can run. Large language models that have been trained in various ways, have been instilled with various biases throughout their training. And these models, they all share one thing in common. That's the data that they're trained on. Well, the type of data that they're trained on. They're obviously trained on different sets of training data. What we did with GPT4All is we were sort of the first large scale, the first model that performed a large scale what's called distillation from a larger model, specifically ChatGPT. So what we did is we went and generated a large collection of questions. So questions that we wanted to ask ChatGPT and record its responses. And then we use those examples of inputs and outputs to go in and generate out the actual to go in and create a training set to train the local large language model. And just to give you an example of what this sort of data looks like, I'm actually going to click on this link. This is actually a picture of the training data set. So if I go in and I load up this link here, you'll see this is actually the training data set for GPT4All J, which is the GPTJ version of the data set. And you can see here there's like types of questions that the model was shown as examples to learn how to be a question answering chat model. So what is air pollution? What are the causes of it? And then the answer that ChatGPT gave. And so in general, and then you see here, there's also examples of code. I have a code query to write down, and the model writes out a code. This is actually code to train a machine learning model. Interestingly enough, there's examples of writing spooky stories. So this is sort of showing the data distribution that was trained. This is actually another Nomic project called Atlas, but that's not important here. So whoopsies. Okay. So the basic idea is that you need lots of high quality curated data that matches the sort of chat format if you want to get your own local large language model that you can perform chat with, just like you can perform chat with OpenAI's models. And in this specific model, we go in around, as I said, using multiple diverse types of data sets, coding questions around general sort of human behavior, these sort of things. And then what do you need to actually train it? So you have this data set of examples of conversations with a larger model like ChatGPT. If you wanted to do this nowadays, I'd distill from something like GPT-4 or use the plethora of training data sets available on platforms like Atlas or Hugging Face to go in and get your own data. most of these data sets are released in ways that allows you to train the model and then be able to run it in a commercial setting in production. So what does it take to actually train the model? Well, you need one of these big boxes that I showed you earlier that I said was super expensive to buy. Usually people don't buy these boxes; they rent them. They go to a service like usually you don't want to use a cloud provider like AWS or Azure. They charge way too much. You want to use one of these sort of like smaller companies like Paperspace or Lambda Labs or CoreWeave. You can go in and for $20 an hour rent one of these boxes. And to train one of these models, thankfully, you don't have to. There's techniques to allow you to train them pretty cheaply. So with this data set of about 1 million examples and the 7 billion parameter large language model, at the end, it only takes about $200 US dollars to get one of these models trained. And if you think about it, depending on what you're using it for, that's a pretty good deal. As the models get larger, if you want to do more fancier things, it becomes a little bit more expensive. Truly, it is the case that you're going to want to train it a few times because I guarantee you the first time you're going to make an error. So maybe the cost will have some constant in front of it, but the constant will be greater than one and less than probably two or three. So you need some serious hardware to train these things. This was the case in last April, last May. Currently, there's techniques that allow you to do this on less intense hardware. If you have 3090 or 4090 GPUs from NVIDIA, there's some stacks to be able to do this yourself. But the easiest way is to go in and rent one of these big boxes. They work with most of the open source training frameworks, specifically the training logic that we have in GPT4All to be able to do this. And then there's one more trick. There's one more trick to be able to make these models run locally. Make these models be able to run in the manner that I just showed you on my local laptop while I'm also running a pretty memory and CPU intensive software to stream this presentation over to you guys. The one trick is post training weight quantization, and those are big words. But what it means is basically you take all of the parameters that exist in that machine learning model, all the knowledge that it's contained in it, and then you prune it a little bit. So that means you cut off pieces of information. What this means concretely is that when you have a 32-bit floating point parameter, what you can do is you can represent that parameter in many less bits while maintaining the quality of the model. And you might think here, right? If I take 32 bits and I cut it down to here specifically, these models usually run in 4-bit precision. So that means there's only 16 possible values per weight instead of 2 to the 32nd minus 1 different possible floating point numbers per weight. You might get significant degradation in model quality. What it turns out to be the case is that in order to train a large language model to high performance here is measured in this metric called perplexity, lower is better. You need to have this full precision, 16-bit or 32-bit floating point operation precision. But to actually do model inference, you don't need that. So the training dynamics require high precision training, 16-bit, 32-bit, but the inference dynamics, it turns out to be the case that as models get larger, you can go in and delete a lot of the parameters of the model while maintaining the model's quality. And this makes it cheaper to run. This makes it less resource intensive to run. This allows you to run the models on a device that's akin to something like a toaster, a low resource device with low amounts of memory and RAM. And to give you sort of a more precise view as to what it actually looks like and what kind of model sizes does it make sense to do something like post-training aware quantization for a transformer decoder, you're looking at about 6 to 7 billion parameters. After about 6 to 7 billion parameters, what happens is that the difference here, this delta, you wouldn't look at this delta between the red line and the dotted black line, goes down to such an extent that it becomes almost unnoticeable, the performance difference between the model in full precision and 4-bit precision. I'm not going to dive too much more details on how these. Actually, I will. There's one more slide on exactly how this post-training aware quantization algorithm works. So this will be sort of like the most in-depth technical part of this talk. So if you get lost, no worries. It gets there's light at the end of the tunnel. But the whole idea is that in order to train a big neural network, you need the high precision parameters. In order to actually infer it, you can throw away most of those parameters, and it turns out most of the knowledge is contained in probably a small subspace of the model's parameters space. And how these algorithms actually work. So this is a little bit of math, so don't be scared. But what you see here is this equation that basically shows you something akin to a linear regression. So the whole idea is that you have a high precision block in your neural network. So you have parameters that are all 32 bits. And what you want to do in the neural network is preserve the outputs given the inputs. So you want to make sure that for a given set of inputs, the high precision outputs are the same as the low precision outputs. So what you usually do is you go through the process of quantization works by sampling a set of possible inputs to your model, so this would be a set of possible prompts or examples to your large language model, and then running those examples in high precision. And then what you do is you can go in and you define the set of possible low precision parameter states. So for every single parameter, you have 16 possible options for each parameter, as opposed to 2 to the 32nd minus 1. And you try to preserve the input output matching of the model, but constrained to the fact that you only have 4 bits per parameter. And then you can solve basically a convex, in this case, a convex optimization problem. So you use a machine learning model. So you use a machine learning optimization algorithm to go in and perform the post-training quantization on your machine learning model. And that sort of like gives you some idea at the high level exactly how this sort of technique works, why we can go in and delete most of the parameters and the model's quality is still retained, because we're really matching the inputs and outputs still. It's just the function in the middle is changed to be simpler in such a way that it's representable easily in the computation of like things like CPUs. Cool. So where are we? So what is GPT4All now? GPT4All, it's basically a collection of clever C++ code that allows for efficient inference of quantized large language models. So there's logic implemented, so the custom GPU kernels and custom CPU logic to be able to go in and run these sort of quantized weights really efficiently on modern day CPUs. So most of the sort of backend is actually built over this framework called GGML. So GGML is this TensorOp library that lets you do quantized tensor operations on CPU. So you might have heard of Llama CPP, which is sort of like one of the leading projects out there using GGML. The creators of both projects are the same. And what we do is we actually maintain a fork of this Llama CPP repository. There's a few things about it. So it's sort of a very dev and experimental repository. What we do is we maintain sort of a more stable version of it, and we make it really accessible. So like our focus with GPT4All is to make technology super accessible for anyone non-technical. So the whole idea is that we make training the model super easy and super accessible, and inference of the models. You can go in and just download a chat application that runs on your Windows machine, your Mac machine, your Linux machine, and you click 3 buttons and you get an installer working. You can go in here. The instructions are pretty simple. Just you can navigate to the GitHub page or go to gpt4all.io to get up and running. Super easy to do. And all the models there are basically trained to the procedure that I showed you. You want the GPUs, you want the data, and then you want to do these couple tricks at the end, like post-training or quantization, that lets those models run fast locally. And what kind of the most important things with these models is that they're Apache 2 licensed. So what this means is that, if you want to build a business over top of the code that you get to use in GPT, you have in GPT4All, you're welcome to do that. So it's really sort of like the one of the easiest ways to be able to safely build a large language models, knowing that if you wanted to go build a business over it, you can do that. We don't restrict what people can do with the models in GPT4All. So that's pretty exciting. It was not the case before this. It was the case that if you wanted to access this technology, you had to go through third-party servers like OpenAI. We really, when we say democratize access to artificial intelligence, I really mean it. And there's a growing developer ecosystem. We have the fast C++ core that allows quantized LLM inference on both CPU and GPU. We have Python bindings, JavaScript bindings, Golang bindings. There's a large community of open source contributors in our Discord of about 25,000 people that help maintain this. We have Docker-based images if you want to deploy these models on servers. We have several blog posts that talk about sort of like the best ways to deploy these models for different sort of performance use cases. If you have high user concurrency, if you don't have high user concurrency, there's a giant stack and a giant set of methods that you get to pick from depending on your use case. Obviously, it's not a one-size-fits-all thing, like anything in software. And sort of most excitingly, and this is what I'm going to sort of end the presentation on in a few minutes, and this is our support for GPU inference. This is a project that was being undertaken by the open source community around GPT4All, spearheaded by some of our developers at Nomic. doing adding support for quantized GPU inference. And when I say GPU inference, I don't just mean the most top of the line NVIDIA cards that cost $2,000 to buy. We really doubled down on the accessibility angle, and we wrote GPU inference to be able to work on AMD, Intel, Qualcomm, Samsung, and NVIDIA GPUs, all open source, available in GPT4All. So how does this actually work? So how do you make large language models run on all of those different types of GPUs? Well, you want to really rely on the rest of the open source community. If you guys have ever heard of OpenCL, the successor to OpenCL is something called Vulkan. Vulkan is this kind of GPU API language. So you write code into the Vulkan API, and then it gets compiled down into all of the target GPU languages like CUDA for NVIDIA, ROCm for AMD, etc. And what we did is we went in and created a giant effort to replicate all the tensor operations that run in a large language model, but in Vulkan. And in doing that, we've been actually able to allow a giant new class of individuals to run these models a lot faster on their everyday devices. So it is the case that most devices ship with like an Intel integrated graphics card, like most consumer grade laptops. It is the case that a lot of people have AMD GPUs because historically AMD GPUs have been really cheap because NVIDIA has outperformed them on the software side. A lot of people have these cards, but before we did this, nobody was able to really use them for efficient inference of large language models. And we're not the only ones building in this community. To be clear, there's a lot of projects that work towards enabling access to this tech, especially enabling access to solid GPU support for inferring large language models. But we really do strive to be the one that's easiest to access for people. It's super easy to get set up. The GPUs get automatically detected in your machine. If you want to go in and build with it in some sort of programming language, we make that super easy as well. And what does this really mean at the end? This means that anyone can really easily download and run large language models on lower end consumer grade GPUs, and we get to increase the accessibility of the tech. And just kind of show you how fast these things are. So this is a table that's demonstrating to you the sort of inference time. So how many words, how many tokens per second the models can generate. So what you're looking at here, there's kind of three classes of models. The names aren't that important. Llama 2 is that sort of open source Apache 2 license model that, well, it's not Apache 2 license. There's an addendum to the license. But it's an open source model. What you want to look here is the parameter sizes: 3 billion, 7 billion, 13 billion parameters. And as you can see here with the Vulkan backend that we maintain in GPT4All, we sort of get we actually beat OpenCL in inference performance on the latest NVIDIA GPUs. We support AMD GPUs. It runs really fast on Intel CPUs, 20 words a second. The demo I was giving earlier of running on my MacBook, that's actually using something called Metal. So this is Apple Metal Acceleration. Apple Metal Acceleration, what it allows you to do is utilize those M1 and M2 chips sitting inside the latest MacBooks. And I was getting about 60 tokens per second generating you that story about Devoxx Ukraine. And as you can see here, these metrics are an underestimate of that. And then we, for fun, ran it on the latest, greatest GPUs, and obviously NVIDIA still smokes everyone in speed because they have about a 10-year head start on every other company in terms of inference. And if you want to use it in your code, there's various bindings for it. The easiest one is Python. You can literally go in, you load up one of your models. So this is a model called Orca Mini. That was actually the one I was just showing you run right there. You could literally replicate everything I just ran for you in Python. And the way you do it is you say device equals GPU, and magically the open source code base handles the rest. You go in, the GPU gets automatically detected, it gets run. You have to know nothing about how the GPU works. Easy as pie. And how many models can you use? Well, you can use roughly 2,000. Actually, this is a slide that I put together. I updated yesterday. So if you go on anything that's built, so it's anything that supports GGML or GGUF. These two tensor formats that allow for fast quantized CPU and GPU inference. Any of these models you can download, drop into GPT4All, and then boom, you're playing around with a multi-billion parameter large language model on your maybe not top of the line laptop. And then sort of kind of a few things I want to point out. It's really, really important. So how do all these models differ, right? What is the difference between all of them? which one do I use? Well, it really depends on data quality. So the kind of data that was put into the model. The way you program a large language model is you program by manipulating the data that goes into it. You put in different data into the model. You can instill different biases into the model. OpenAI put really, really high quality data into their model. They spent millions of dollars paying companies like Scale AI to go in and generate out high quality stories, high quality essays that they use to go in and train these models. They have a very high quality model. It's really expensive to do so. Poor data leads to model reliability, increases hallucinations, and it's important to go in and curate your data. My company, we have a product that allows people to go do this. I won't talk too much about it. It's called Atlas. It's kind of the graphic I showed you right there. But it allows you to really easily go in and do this sort of data curation process, and to sort of just give you a statistic. About 60% of all of the data that we originally scraped from OpenAI to be able to train the first GPT4All model wasn't actually used to train the model. We curated it out because we deemed it to be too low quality or heavily duplicated. When you show duplicate examples to a model, it makes it do bad things sometimes. So we only used about 400K samples to train the end model out of the million samples that we were able to scrape from OpenAI, which is sort of an interesting fact a lot of people don't realize about large language model training. And then where are we going? Increasing developer accessibility and increasing accessibility to increasing non-technical individuals. I want us to live in a world where there's a large language model running on every single computer that's powerful, that can be accessed locally. You can turn off your internet and you can have access to the technology. We're going through and building up a stack that enables that. It should be easy to do. You shouldn't be a highly technical person to be able to access this tech. And we're doing tons of things both on the accessibility front and on the software front to enable access to powerful local large language models. And then sort of like the final question, this is sort of the thing that a lot of people, their first reaction is when they try a local LLM, they respond with, wow, this is so cool. I'm going to keep using OpenAI because these models stink. They're not good enough for what I want to do. And this is the case. There are many examples where you still need to use closed source large language models because they are better. They have been trained with more resources. They have been they're higher quality. The models are usually much larger. So a 13 billion parameter large language model is actually pretty small. Chat GPT, or at least GPT-3, who knows how large the models are now or how small they are now, was 175 billion parameters when the research paper came out. So that's an order of magnitude larger than these models you can run locally. And they're very useful. The local models are still very useful for single tasks. If you want it to be a general purpose model, do everything all in one model, like you can get with a Chat GPT. That's a little hard. The models can't do everything, but specific tasks they can do really well. If you wanted to do summarization, or if you wanted to train it to specifically do one form of text manipulation that you need at your company, that's all really possible. So what does it take to get a Chat GPT like quality model on your desktop? So what does it take to get these local models being the quality of OpenAI's models? There's several things. You have to train these models. You have to train these smaller models for longer. There's several sort of companies and initiatives to be able to do this. There's a whole army of people working towards a future where access to this technology is not held behind the hands of a few closed source companies. And it's really exciting for me to be a part of that and to be able to have some say in this community, to enable people to be able to use this without having to have expensive devices and expensive machines. But we will be in a world where a call to a large language model is like a Linux kernel operating system, like a Linux kernel system call on the Linux operating system. It will really be the case that every computer ships with a large language model built into it, and you won't have to be calling third-party APIs. For now, the case is the fact that you do. But there are many directions that you can go to the world can go for us to get there. We need higher quality data sets. People are working on these higher quality data sets. We need freer access to compute. People are realizing this. There are large projects that enable organizations that have these data sets to be able to access compute without having to pay millions of dollars. People are working in this direction. Your next iPhone, your next MacBook will ship with large language models inside of it if they don't already. Awesome. So that's about it that I have for you guys. Thank you so much for listening. I hope you learned something new. And I really hope you guys try it out. There's a lot to be learned in the world of running large language models locally. There's a lot of fun to be had. And there's a lot of interesting businesses you can build over top of this technology. And I'm really excited to be able to play some part in helping increase access to it. So just kind of one last thing I want to say. We are actually hiring for a systems engineer at Nomic. If you're interested to apply, if you have a machine learning background or if you have a systems engineering background, you can go to careers.nomic.ai to sort of find information on that. And yeah, open source the data, open source the models, GPT for all. Thank you.
Thank you, Andriy. No questions in the chat, so let's hope that everything was clear. Otherwise, I hope that our participants can reach out to you somewhere that you are reachable. And once again, thank you for joining. Thank you for your talk. We do appreciate it so much for your support.
Yep, thank you.